Okay, boys. The log laws are, as you would know, linked to indices. So they're another way to express an unknown. And what I've done to make it easier is I've tried to color coordinate the different components. So what we've got is a log law that says the log to base A of two unknowns, which is x and y, can be separated into the log of them individually. So log ax plus log ay. So in order to do that, we're going to start by not considering the logs being involved. So we're going to let x equal a to the power of m. Now the reason we can allow that and y to be a to the power of n is because we are going to essentially link log to indices because logarithms are indices. So if you remember year 8 log laws, this is where it's going to use this information to prove our new formula or law. Okay, so if x in the purple is equal to a to m, and we'll let y equal a to the n, if we take log a base a, what we're asking essentially is x's value is equal to a to the power of m. So we can re-express that by taking the log of both sides, and you'll get log to the base a of x is equal to m. Similarly, log a to the base y, base a of y is equal to n. So if we multiply these two, x times y, you'll see that that really means a to the m times a to the n. Knowing your indice laws, when you're multiplying indices of the same base, you just add the indices. So that is how we get a to the power of m plus n. Again, to get logarithms without to the power of m plus n, we are allowed to take the log of both sides. So log a in the green there will eliminate that unwanted base of a and bring the powers down to become the subjects. Therefore, log a of xy is equal to m plus n. And if you look up the top right there, we had our purple and like orange color here. That's them re-expressed there. So m plus n is equal to log a plus log a to the power of a to x plus log to the power of a to the n. That's the same as what we have up here in the box. Next, we've got a similar law, which I've similarly color-coded. And you'll see here that it's basically the same except for when division's involved. So up here we had multiplication. Now we're looking at division. And our indice laws are again used, except we now, when we're dividing, our indice laws tell us that we subtract the indices here once they're under the same base. So following the process through again, the only difference here is that it's m minus n. Okay, because of this division, our indice laws tell us that it is subtraction. So that's the proof of that one. It's the following, follows the same idea. Finally, we've got another law that says log a to the x to the power of p. What we can simply do is take that p down the front, okay? And how we do that is we don't involve any value of y here, okay? So it's not combining two unknowns. It's concentrating on the movement of a logarithm to the power of a value unknown. So here we let x equal to a to the power of m, and we similarly take the log a of both sides to get log a to the x is equal to m. We use this in the purple here later on. So if you let x to the p, essentially raising this side to the power of p, you'll see that that indicates that we're going to raise this to the power of p as well. Now you should know from the indice laws that any indice which is multiplied in the power, we just simply multiply the two indices. So m times p. Taking the log a of both sides, this a in the green will disappear. We'll take the log of this side here, and that'll reduce mp down to a format that we can use, knowing that here m is equal to log ax, subbing that in there, that proves it simply by having anything to a log to the power of another value, we can simply take that down the front and multiply it. And therefore, that's how we get p log a to the x. Over the page, just bear with me, we've got some more logarithms and they can be proved, though I'm not going to do that for you now. What I'm going to explain to you is actually how we already know these. So if you consider this one here, we have log a to the power of 1, we've got to find some value that when we raise a to the power of this value, we get 1. So we should know that anything to the power of 0 gives us 1. Similarly, this here, that's asking the same question. The log of a, so how do I get to a? What do I raise it to? It's to the power of 1. If you follow that format through, all these will just simply cancel out. And it's not cancelling out in that sense. It's simply allowing the fact that you're taking the log of the same quantity, a log a of a. And if you remember from our previous rule, that x comes down the bottom. Using this rule here, we will get a value of 1. So that's like having x log a of a, which is 1. So that's why we get x. Finally, if you consider log a to the power of 1 minus x, that will tell us from our previous proof that log a of 1 minus log a of x is equal to this. That is what we said. And that's because it's a division, and that's because we have our indice law. When we have a division, we subtract the powers. Now, log a to the power of 1 over here can be c as 0. So we've essentially got 0 minus x. So 0 minus the log a to the x using the rule, and therefore 0 minus anything, we just write what it's minusing. So those are those 4 rules. Like I said, you won't probably be asked to prove them, but understanding where they come from is a big assistance in solving problems.